All right, let's talk domains where a function is allowed to live. First, polynomials. These are your nice functions. It has the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2, etc. Right, so these functions are, for example, they are quadratic function, cubic function, quartic, meaning function with the degree of 4, or quintet, right, degree of 5, etc. No square roots, no denominators, nothing sketchy, right? Because the nothing that can break the domain of any polynomial is all real numbers. Meaning you can plug in any real x and it will make sense. The function is smooth, no breaking, no stopping, no sharp point, no loop, no hole. Smooth, right? You put your finger across a function is very smooth, right? It won't cut your finger. Let's take a look at the example on decimal to see what I meant by that. All right, so these polynomials here are the one from the lecture notes. Take a look at the first one. This is quadratic. As you can see, as the two arm, it has a shape of parabola, by the way. As the two arm extended, it gets wider and wider. Of course, you go to positive infinity. You can always find an x, right? That project to the function. Same thing here. These cubic function, it look like a railroad track here, but again, everywhere you project, if you try to project a value from the function to an x-axis, you can always find an x values, right? As the arms extended, to the infinity. By the way, domain. Remember domain? We talked about domain is make up all the x value, right? So we focus on the x-axis here. Okay. Here's a quintic here. All the odd polynomial function, it looks like a railroad track, except its degree get higher. It get flatter at the waist here. Okay, so same thing is similar to the cubic function. Okay, so as you can see, these functions are quite smooth. So you can zoom it in a little bit. It's quite smooth. There's no sharp point or stoppage or loop or hole here. So the domain of any polynomials is all real number, and if you represent in notation, it's going to be a negative infinity to positive infinity. Okay. Now, rational functions look like a fraction. It has a form p of x over q of x, like that, where q of x cannot be 0, right? You don't want 0 in the denominator. The only way they misbehave is when the denominator equals 0. So the domain is all real numbers except the values that make the denominator 0. So our job is simply to find and exclude those values. Right, so to find the domain of a rational function, let me highlight it here. We set the denominator equals 0 and solve for it. Whatever end result, that's those values, you exclude them from the domain. So they'll make the denominator 0. Let's practice. I have 9x minus 9 over 2x plus 7. We're going to focus on the denominator. So first we're going to set, so light, make it a little bit darker. We're going to set 2x plus 7 which is 0 and solve. This is linear equation. Everybody should know how to solve the x equal negative 7 halves. Right? So it means we exclude it. We don't want that, right? So on the number line, if we draw this on the number line, right, negative 7 half right here. Now, we don't want it. Everything to the right of negative 7 half or to the left of negative 7 half are fine, right? Any values to the left or right of negative 7 halves are fine. as long as it's not negative 7/2. Right? And let's write it in interval notation. So from negative infinity to negative 7/2, parenthesis, meaning the parenthesis, we don't include the negative 7/2. Union, negative 7/2, we start there again. Of course, we don't include it to infinity. If you give me interval notation like this, I'll give you an extra credit on your homework, okay, or your exam. Part B. Again, we focus on the denominator. We're gonna set 3x squared minus 5x minus 2 equals 0. And I'm going to factor here. Do you guys remember how to factor this? Remember this? By two number multiply to negative 6. Remember the product is negative 6 and the sum is negative 5, right? That will be what? Negative 6 and 1, right? And then what we're going to do is we're going to split that negative 5x into negative 6x plus 1x, right? So 3x squared minus 6x plus 1x minus 2 equals 0. Group factoring, remember that? Group factoring. Factor out 3x for the first group here, so I have x minus 2. Factor out a 1 here, so x minus 2 again equals, I'm running out of space, I'm not going to do. So factor out x minus 2 here. What remains is 3x plus 1 equals 0. This implies either x minus 2 equals 0 or 3x plus 1 equals 0. Right? So x equals 2 and x equals negative 1/3. Or rather, not equal to, right? This is what we don't want. So on the number line, it looks like this. Negative infinity, positive infinity. Negative 1/3 comes first. It is negative numbers. Stay to the left, and 2 here. We don't want these 2, but anything in between is fine. We take anything in between, right? So as you can see, there are 3 intervals, okay? From negative infinity to what? Up to negative 1/3, not including negative 1/3. Union from negative 1/3 to 2, right? Of course, not include those 2 ends. Union to infinity. I also accept this, by the way. If you stop right there, that's fine too. But extra credit will be interval notations. Okay. All right. Let's take a look at these rational function on decimals. Here, the first problem we did. Zoom in a little bit. As you can see, remember what our value we found it x equal negative 7/2, right, or negative 3.5 here. As you can see, this dotted line here, that's the function. That's the function x equal negative 3.5. So yeah, around that area, as you can see, at negative 3.5, the functions goes ballistic, right? On the left side, it's kind of go shoot up to infinity. On the right hand side, it's kind of dip down to negative infinity. Okay, so as you can see, in this part here, it makes no sense. Second one, B, part B, we found that x equal negative 1/3, and x equal 2. There you go. Same story, right? We have a huge gap at negative 1/3 and 2. It's not as smooth like polynomial. Radical functions. Before we actually jump into its domain, I want to recall something. If I have a generic radical like that, right? This part underneath the root is called radicand, and this black thing will be the root, and here will be some number here will be the index of it. Square root, there'll be 2, but we don't usually write the 2 there, right? The q will be number 3, 4 root will be 4. Those are index. Okay, now the domain of a radical function with an even root is all real numbers that make the expression inside the root greater than or equal to 0. Remember, square root does not like negative number. If it has negative number under the square root, it turns into imaginary number, which is we don't want to go into that land, right? So it has to be at least 0. For an odd root, like cube root, then the domain is all real numbers. But we're not gonna get into that. Don't worry about this part. I'm just don't worry about this. I'll just right there for you to see. We're gonna focus on the domain of the square root. So let's take a look at 2a here. I have 1 over square root of z minus 1. Okay. So first of all, z minus 1 under square root. So I know that z minus 1 has to be at least 0. Right? And second thing is that because z minus 1 is in the denominator, then it can also cannot be 0 either. So if you combine these two, what do you get? Z minus 1 has to be exclusively greater than 0. Does it make sense? Right? The square root say, yeah, you can be 0, but then because the location is in the denominator, then it cannot be 0. Then you combine those two, it has to be exclusively greater than 0. Then you solve this inequality. Right? And then what does it look like on number line? Infinity, positive infinity. 1 here, we do not want to include 1, so we hollow dot, right? And we want everything to the right of 1. And that'll be your solution. That'll be your domain. So the domain from 1 to infinity. Okay. All right, part B. I'm going to focus on the denominator first. I always focus on the denominator if I see fraction. So I have x plus 1. Well, of course, x plus 1 is equal to 0, and x plus 1 cannot be 0. So, combine those two together, just kind of like the one on the left. But I'm going to do it all at once here. So x plus 1 exclusively greater than 0 because it's the square root and is in the denominator. Right? So this implies x greater than -1. And then for the numerator, I have x minus 2 greater or equal to 0. It doesn't have to be not equal to 0 because it's in the numerator, right? You can have 0 in the numerator, and that's fine. And x is greater or equal to 0. I'm sorry, 2. 0. All right, let's combine these two results. I have -1 here. I don't want to include -1, so hollow dot. And I have 2 here. I can include the 2, so solid dot. Right? So the red part saying that x had to be greater than -1. And the blue part saying that x is greater or equal to 2. And we're going to choose the overlap one, right? Because we want to satisfy both. We don't want to plug anything between like -1 and 2 into the function above, and then the numerator will scream, right? Like you say, I'm not defined there at that region, right? I'm only defined anything that's greater or equal to 2. Okay, so we had to pick something that they both have in common. So your solution will be from 2, include 2, so we use bracket 2 and 3. All right, let's take a look at these radical function on decimals. Here's our part A. As you can see, remember we found that x has to be greater than 1, right? So as you can see here at x equal 1, because you don't see this line, just put it there for you. The function don't cross that bridge, right? It's kind of start at 1, not touching 1. If you zoom it out, it looks like it's touching, but it's not. It's never touching. See, it looks like it's touching, but it's not. And go from there to infinity. That's where it lives. For part B, let me mute these. Part B, we found that the domain is x is greater or equal to 2, right? And there it is. It start from 2 and go to infinity. Okay. And that concludes our section of domain of functions.